Hello everyone, and welcome to this session where we're going to talk about querying your data lake. My name is Russell Nash and I'm a solutions architect with AWS, and in this session we're going to talk about using S3 as your data lake and some of the different tools and techniques you can use to query that data. So let's talk first about using S3 as your storage layer. So S3 has some really key features that make it perfect for use in a data lake. First of all, it's an object store, and this means that you can load up pretty much any type of object that you like into S3. Secondly, it's very low cost, and so this is important as your data volumes grow. You don't want the cost of your storage layer to be blowing out. It's highly scalable, so you don't need to pre-provision space within S3. You simply load up data as you need it. And importantly, we offer you 11 nines of durability for data that goes into S3. And we're able to do that because every object that you give us, we actually copy multiple times to multiple locations to ensure that we can give you 11 nines of durability. So when you load up data into S3, you then don't also need to back it up. You've got that durability taken care of for you. So let's look now at some of the framework that we use to discuss modern data architectures. So if you look at this framework, you can see several different boxes here, and let me talk you through them quickly. So on the far left, we have the different sources that we're going to load into our data lake. We're then going to look at how you ingest data into the lake depending on the sources that you have. Then in that top box, we're going to look at the different options for batch processing and how you do that. The box below that you can see is the speed layer or the real-time layer. And then on the right, we'll be moving into the serving layer. And the serving layer is where we then make the data available to the interested parties on the far right-hand side there. So you'll see your data analysts, your data scientists, and some downstream applications that want to access the data into your lake. And it's the serving layer where we'll be spending most of our time in this session. So let me talk you through each of these boxes in turn. So in terms of the sources that you have, most customers have a variety of different sources, and I've just put a couple onto this slide for you. So you can see you've got highly structured data that might be living in databases, for example. There might be flat files in your organization. You may have log files, for example, that come from hardware, from servers. You might have device data, mobile data, location data, or clickstream data, for example. So just an example of some of the different types of data that you could have in your organization that you want to get into your data lake. So let's have a look now at some of the ingestion options for some of those different sources. So what you use for ingest will obviously depend on the source of data that you have. And so some of the examples I have here are, for example, ETL. So that stands for extract, transform, and load. And this is a number of different tools out there on the market. We have a number of fantastic partners in this space, and that can help you to get data out of highly structured databases, for example, and into your data lake. You can see DMS there as well, so that's our database migration service, and that's our own ETL tool that you can use for accessing certain sources of databases, again, to get data into your lake. There's also a number of open source tools that you can use. So we have things like FluentD, Log4j, and heaps of others that you can use to get data into S3. If you happen to have an enormous amount of data on premise that is too much to push down your internet pipe, then you can use something like AWS Snowball, for example. So this is a physical device that we will ship to you. You can load your data onto it, ship it back to us, and then we will load that data up into S3 for you. And that last one down the bottom you see there is Kinesis, and this is the service that we use to deal with very fast moving data, streaming data, if you will. So let's move on now to the batch layer. And the batch layer you can see there typically consists of moving data into S3 and then transforming that data with some kind of processing engine. Now most people like to use Hadoop in this particular place in the architecture. And so we'll talk about Hadoop and we'll talk about EMR as well as an option a little bit later on. So whatever tool you use for transformation, that data is then picked up from S3, transformed, and then put back into S3, ready for the serving layer. But what about streaming data? How do we deal with that? So if you look at the box below the batch layer, you'll see the speed layer there. And in here, data is typically captured with Kinesis, and it is then you have the option to process it however you like. So you can see a couple of options there. You can either create an application, so that application will run on EC2 machines, and that gives you tremendous flexibility with how you deal with the data that's coming off the Kinesis stream. Now, a lot of customers are obviously moving to serverless architectures, and so you'll find that in fact, instead of using an application on EC2, they prefer to use Lambda, for example. And Lambda is a service where you simply give us your code and we will run that code for you. There's no servers to manage there. So you can run that code in response to an event that happens, for example, or you can actually point it to a Kinesis stream and the Lambda function will poll the stream waiting for records, and then it will kick off your code once that record is available. Or you may want to use open source tools as well. So there's tools like Apache Spark and Flink, for example, also very popular as stream processing engines taking data off Kinesis. Now the outputs for this real-time data is obviously going to be things like real-time dashboards. So you may want to load things into Elasticsearch, for example, but also you might want to do predictive analytics, and you want to do this very, very quickly, which is why you want to point this at the near real-time stream. For our purposes though, we want to take the real-time data and we want to move it into S3 because we want to marry that speed layer with the batch layer so that we can then make that available to the serving layer. So let's move on to the serving layer. So there's lots and lots of different options that you have for querying data in the serving layer, but I want to touch on three main ones today with you in this session. So we're going to have a look at Amazon EMR, we're going to look at Amazon Athena, and then we're going to touch on Amazon Redshift as well. So let's look first now at Amazon EMR. So EMR is our managed Hadoop service. And so this means that we actually manage the Hadoop stack for you. It is highly optimized with S3, and we'll talk about how that works and why it's important a little bit later on. And it's also got very strong open source support as well. And this is really important to you because if you're using open source tools, you want to be using the most up-to-date versions of those tools. So when a new version of Spark comes out, for example, we work very hard to get that into EMR as soon as we possibly can to make sure that you're using the versions of Spark that you want to use. So EMR very, very strong with open source support. So let me show you this in a little bit more detail. So here we have a typical Hadoop stack, and you can see down the bottom there, starting from the bottom up, we have the infrastructure layer. So if this was on Amazon Cloud, for example, these machines would be EC2 machines. You then have a data layer, so typically that would be HDFS. And then you have the process layer. So this might be MapReduce, it might be Tez, it might be running Spark, or potentially a combination of all two or three. Then the framework is Hadoop, and then of course on top of that, you've got the applications that you want to run. So typically most of our customers will use those applications at the top layer because they're much easier to use than writing down at the process layer, for example. And those applications, as many of you would know, there's a very rich ecosystem of applications out there, whether it gives you SQL-like layers on top of Hadoop, or NoSQL layers, or machine learning, etc., or transformational layers. Those applications, very, very rich, supporting lots and lots of different workloads. So where does EMR fit into this picture? If you look on the left-hand side there, you can see that's where really EMR sits. And what EMR does is it manages this stack for you. So this Hadoop stack, you could spin it up yourself. So you could spin up EC2 machines, you could install Hadoop, you could configure it, you could then install the applications, make sure they were all working together. But there's a lot of heavy lifting involved in doing that. So what EMR does is it manages the stack for you. So you talk to the EMR console or through the API or the CLI, and you tell EMR that you want a cluster of a certain size, certain applications you want installed, and you let EMR do the heavy lifting of bringing up the cluster, managing the cluster, and then you simply get to use the applications. So the end result is you're still using the open source applications as you would normally, but you've spent a lot less time and energy actually getting the cluster up to that point. EMR also brings another really strong benefit with it as well. And that is that it allows you to use S3 as a data source. Now what we've done there, you can see on the slide we have something called EMR-FS, so EMR's file system, and this allows EMR to work with S3 in a highly optimized fashion. And what this then does is it opens up all those applications to then start using S3. And so you can imagine in our data lake scenario where our data is in S3, that's extremely important. So let's look a little bit more closely at how some of these applications actually query data from S3. Now, Hive was the first SQL-like layer on Hadoop, so we're going to start with that. And let's say you have data in S3, and you also have users who want to access that data. So you spin up a cluster with Hive on it, and the first thing that needs to happen is you need to create an object that points to the data so that you can query it. So you run a create table statement, as you can see here, and what that does is it creates a table in the catalog, and this points to the data on S3. Now at this point, no data is actually moving. We're simply creating an object that is then pointing to the data. But what we now have is an object that looks like a SQL table that allows us to use SQL to query the data that's sitting in S3. So now you can see the users can run SQL statements, and Hive will convert and extract the data from S3 before returning the results to the user. So a very powerful way of letting people familiar with SQL get access to data in S3. Now what happened over time was that Hive was found to be a little bit slower than people wanted it to be. It wasn't quite as interactive. And so other tools sprang up that still gave people SQL access, but in a much faster fashion, a much more interactive type of speed than Hive was doing. However, it made sense that these tools used the same catalog that Hive was using. And so you can see here we've got Spark SQL and Presto and Pig, for example. And the idea is that once you create the table in, say, Hive or Presto, you can then access it from multiple engines. And that's really important that we share that catalog amongst the different engines that we have. Okay, so let's move on now to Amazon Athena. Now you've heard me talk a little bit about Presto, and Presto was a tool that was designed really to also give SQL access to S3 and HDFS, but to be much, much faster than Hive had been, to really give people an interactive type of experience. So Presto is popular because it's fast and it's also easy to use. And what we found was a lot of our customers were spinning up EMR and Hadoop clusters in order to use Presto to access their S3 data. Now, whenever we see customers doing a lot of heavy lifting, we like to try and ease their burden by introducing a managed service. So this is what we did in this case. So we took Presto and we turned that into a managed service. So what Athena allows you to do is to query data on S3, uses Presto underneath the covers, but it's a completely serverless type of service. So you're not having to spin up anything, you're not having to manage a cluster, and obviously you're not patching any clusters. So the way this works in Athena is similar to the way that works in Hive. So first you create the table as you would in Hive, and this sets up the object in the catalog that points to the data. So users can then query that table through SQL. Now, what happens when the query finishes? Well, the Athena cluster doesn't persist, but the catalog does. And this is important. So the server is no longer in the environment, but the catalog, where you've created all of those tables, still persists in your environment. So next time you go to run a query, those tables are going to be there. Now let's move on to Redshift. So rather than being based on Hadoop, Redshift is actually a fully fledged database. It's an MPP database, and MPP stands for Massively Parallel Processing. And this is a breed of databases that they scale horizontally. And that allows you to load up very large amounts of data. They're optimized for analytics, and this allows you to move from very small clusters, from gigabytes, all the way through to exabytes if you need to. It's also fully relational, and this means that you create tables, you create relationships between those tables, and you can move your data model into Redshift and get started very easily. So let's look at how you get data in and run queries within Redshift. So let's say we have some users' data in a file in S3. Now normally with Redshift what we'll do is we'll create the table, that you can see there, the create table statement, and then we will load the data in from S3 using the copy command. And this will actually then load that data into Redshift. So the table can now be queried and the data will come from the local table in Redshift. So we no longer need the S3 data because we have a full copy of that within Redshift. But what happens if we want to use Redshift to query data that sits on S3, but we don't want to have to load it into Redshift first? Well, this is where Redshift Spectrum comes in. So Spectrum is a new feature we've added to Redshift to allow you to query external data that sits in S3. So let's say we have some orders data that sits on S3, and let's say this is a very large file because we're getting lots and lots of orders. So we want to be able to query that, but we don't really necessarily want to load that into Redshift. So what we do is we first create an external table that points to S3, and then we'll be able to query that data without loading it. The real power of this, though, is when we query from both local and S3 tables and join them together. So here you can see that we're joining our local user data that's sitting in Redshift with our big orders file that's sitting in S3. So we get the best of both worlds. So Redshift Spectrum is enormously helpful when you've got large data sets in your data lake in S3, but you also have data within Redshift itself and you want to join across the two. So we've talked about a couple of different options. Now let's compare the options that we've looked at. So here I want to look at 4 different attributes across the different tools. So I've grouped the open source engines together since they run on Hadoop. So that's Spark SQL, Hive and Presto. And I've put a box around Redshift and Spectrum because you can't run Spectrum standalone. You need to have that Redshift cluster running as well. So the first thing I wanted to look at was this notion of schema. So a schema is when we're actually doing the create table statement and we're creating that association between the columns, the data types, and the data itself. And so with the first few options there, we have a notion of schema on read. And what that means is that at the time that we load the data into S3, we don't necessarily have to have that schema created. It's not until we go to read the data that we actually need to do that create table statement. Now this differs slightly from Redshift, where we're loading data into the Redshift local disk, where that's called schema on write. And that means we have to create the table first before we load the data in. Now looking at the cost model, so the cost models differ across the different engines. So if you look at the ones that run on top of Hadoop, you're going to pay for those by the hour because you're running on a cluster and therefore you're going to be paying for that hourly. Athena, you pay for per query, as you do also with Redshift Spectrum. Redshift itself, you also pay for by the hour because it is actually a cluster. In terms of the data store that they support, the ones that run on Hadoop support both S3 and HDFS. And then Athena is S3 only, as is Redshift Spectrum. And then Redshift itself obviously reads off its own local data store. And then in terms of performance, typically Spark SQL and Hive are the slowest out of this group because they're more general purpose engines. Presto is much quicker for SQL queries because it is a dedicated engine that's really been designed specifically for that. And Athena has a similar footprint to Presto because they run off the same technology. Typically Redshift is the quickest because it is a dedicated database. So given those aspects, let's now look at some of the use cases that they would support. So if you look at Hive and Spark SQL, typically they're used for transformational types of queries, more batch type workloads. Whereas Presto is designed for interactive SQL queries across S3 and HDFS, and Athena is similar but in a serverless fashion and talks just to S3. And then Redshift is really your fully featured SQL database. So hopefully that gives you a bit of a feel for when you might use different engines. Now I wanted to finish off our session with a little look at how you tune these engines that are looking at the data on S3. So these tuning tips are for the engines that query data in S3. The Redshift local tables have separate tuning techniques to this. This is really about data in S3, and when you think about it, it's actually more about how you actually control the data in S3 as it is about the engines themselves. So let's look first at data formats. So There are a number of different data formats that you can choose from, and they loosely fall into two main groups. So there's the row-based formats, and some of these are very familiar, such as CSV and JSON, and some of the newer row-based formats like Avro, for example. But then there are also columnar formats like Parquet and ORC. Now you might be asking, why do we need columnar formats as well? Well, it turns out that a lot of the workloads that we're looking at in the data lake are about analysing data. And we found that with the analysis type of workloads, the row-based formats were just too slow. And that's why the columnar formats sprung up, because they're a lot faster. So let's look at why columnar formats are typically faster. So if you look at a simple table, we've got 3 columns here and a number of rows. And you can see how these row-based formats will lay this table out on the disk, typically the way your brain imagines that it will. So it writes out a row, there's a marker, writes out another row, another marker, etc. Now that's fine, but when we run an analytical query, we might say, give me the average age by state, for example. I don't need the ID column for that query, but I still have to read it in order to get to the data that I'm after. So there's a lot of redundant reading going on there. And you can imagine that as your table gets wider, as you add more columns, then this is going to get slower and slower. So how does a columnar format differ to a row-based format? So what you can see here down the bottom is the way that a columnar format will actually write that data to the disk. So it writes out a whole column, a marker, column, marker. So now, when I run my query and I say give me average age by state, I can skip completely the ID column. And again, you can imagine with a wider table, this effect will be even more pronounced. So this is why the columnar formats are much faster for analytical types of queries. So let's move on now to compression. So there are many different types of compression. I've just shown a couple of them here: gzip, bzip, LZO, snappy, etc. But what are the different facets we need to consider when we're trying to choose a particular format? So the first two of these, size and speed, we're kind of used to that trade-off. And so typically any compression algorithm that can compress the data to a very small size tends to be a little bit slower than one that doesn't get you quite the same level of compression. Most customers I talk to in this space are more concerned about speed than they are about size, because they want to make sure that their users are getting the queries back as quickly as possible. In the data lake area, there's a couple of other facets we need to consider. So one of them is the format splittable? And what we mean by this is that can a process reach into a file and actually pull out certain chunks of it? Because you can imagine in a parallel context, you want those processes to reach in, pull out chunks of the file and send it to different processes, which is obviously a lot more efficient. However, if the format's not splittable, then we're not able to do that. That whole file is going to have to go to one processing engine. And the fourth option there is the data format as well. So certain compression algorithms work better with certain data formats. And so, for example, if you choose Parquet, that works particularly well with Snappy. So you may find that your choice of data format actually informs your choice of compression algorithm as well. So let's look now at partitioning. So partitioning is a really important tuning technique that is going to save you a lot of time when you're scanning data in your data lake. So if you look at what we have here, let's say we have some data in S3 and we have a file per year, but we don't have any partitioning in our create table statement. So what's going to happen now when we run our query, even though our query has a where clause, the system has no way of knowing how to skip the files on the disk to get to the data that we're after. It has to read everything, which you can imagine is very inefficient. So how do we avoid reading every file? What we do is we include partitioning information in our create table statement, and you can see the clause there. Now we can skip the files that don't contain the data that we need. We're just going to read the files that we need, and this is extremely important for performance as your data volumes grow. Now before I go, I just wanted to give you a quick word on our high memory instances. So lots of the tools that we've discussed, they love memory. So Spark, Presto, etc. love lots of memory. We have the X1 instance, which contains Intel Xeon Haswell processors, up to 2 terabytes of RAM per instance, and up to 128 vCPUs. We're also working on newer instances as well that have got even more memory than this. So fabulous if you need a lot of memory. Now, talking of Intel, we talk a lot at Amazon about innovation, but there's also lots happening at the chip level too. And Intel have a lot of features built into their chips, which you can take advantage of in the AWS cloud. I've put a couple of examples here on the slide, but check out the Intel page on the AWS website for more details. Now, you can also continue your learning path on AWS with online labs, instructor-led classes, and certification as well. So thank you very much for attending AWS Innovate. We really appreciate your time for this session. Please do fill out the survey so that we can continue to improve, and I hope you enjoy the rest of the sessions. Thank you very much.